What's up guys? It's been a while since I last posted my video. It was this video, yeah, the wedding video. And after a lot of requests, actually there's been no requests. Actually this is a different one, this is more about my degree. And the last time I made a video on my degree was 2 years ago actually, a day in my life. This is not going to be a day in my life, it's actually summarizing my entire 4th year, you could say. In fact, it's summarizing my master's project. So yeah, this video is going to be about my master's project. So I'll show you guys the video of what we had to submit for our project and then maybe talk something about it.
In this GDP, we present the design and manufacturing of a novel hybrid VTOL UAV. This new design aims to improve on existing aircraft by incorporating a collapsible wing, thereby improving the gust response during hover. To evaluate the gust resistance of our UAV, a custom non-linear flight simulation was created and tested for a range of wing deployment angles. To optimize the UAV's design, various forms of computational analyses were used, including CFD and FEA simulations. These computations were further validated with physical experiments through wind tunnel testing and structural load testing to fully understand the aircraft's aerodynamic and structural characteristics. The UAV has a maximum takeoff weight of 4.8 kg and a camera payload of 0.9 kg. The fuselage contains the avionics and was designed to maximize the wing area reduction. It is primarily composed of plywood, balsa, and 3D printed PLA for simple and cheap construction. For better torsional performance during flight, we chose a twin-tail boom design with an all-moving elevator. Thus, the VTOL propulsion system has a H configuration layout, which provides a total thrust-to-weight ratio of 2.2 during hovering flight. The forward thrust is generated by an electric propulsion system. The battery can provide up to 9 minutes of total flight time. For forward flight mode, the main wing has a span of 1.4 meters with a tapered planform. Corner wingtips were also added to improve the aerodynamic performance. The wing is attached to a pivoting mechanism which can rotate the wing about its center, and its motion is controlled by a lead screw. To provide structural support during flight, 2 carbon fiber tubes support the aluminium spar that connects to the wing. The flight simulation can be explained with 3 core sections: the inputs, equations of motion, and gust disturbances. The main inputs to the equations of motion are the aircraft properties and control inputs from the multi-rotor control system. The control system controls the altitude and attitude angles using a combination of proportional and derivative controllers, modifying the thrust and torque of each VTOL motor. These inputs are then used in the equations of motion to find the time derivatives of the aircraft states, which are integrated through time. A gust model then disturbs these aircraft states with linear and angular velocities up to 10 meters per second and 70 degrees a second, respectively. These new states are then fed back into the equations of motion and control system to continue the simulation. To validate the simulation, a half-scale model was built to perform indoor flight testing. During the experiment, different aircraft configurations were subjected to a range of motor-induced perturbations, while their attitude response was recorded. These perturbations were then replicated in the simulation to directly compare the attitude response. For example, for the roll perturbation experiment, the simulation exhibited high levels of similarity to the experiment for a given desired input. Having validated the simulation, we now show the von Karman gust responses of the aircraft in 3 sweep configurations. These results clearly show that reducing the wing area improves the gust resistance with a reduced oscillation, magnitude, and a shorter time to equilibrium, thereby achieving the aim of this project. Future work plans on improving the aerodynamics and including more capabilities in the flight simulation.
So that was my master's design project. It was a group project, as you saw. Well, we built a plane that can go up and forward in one. So planes usually can't do both. That's why our plane was kind of different. And the more interesting thing in that, and what made it difficult in that, was that our wing actually moved. So it would collapse and then uncollapse depending on what we wanted to do. And actually designing the whole thing itself, because it's quite a new thing. So that's what we did in this project. And yeah, this project kind of summarizes the 4 years. It's quite hard but semi-rewarding. We were able to meet most of our goals, not all goals, but meet most of it. And I think it is, from what we were initially expecting, it's slightly lower, but it's still better than what we thought in the middle of the project, because we thought we can't do anything. But yeah, this is the end of my degree, so it's kind of funny to see how this degree is ending, because I still remember that day in my life video. I've only made one video of day in my life, but it's still funny to see how that was, because now it's completely different day in my life. We have very less classes. Now I don't have university anymore, but yeah, 4th year is very different, very difficult, you could say. So what are my plans now? Well, I will be uploading maybe 1 or 2 more videos in the upcoming months. Be sure to subscribe to that, as you'll see some travel vlogs. I don't know if that'll be good or not, but that is the goal. And yeah, that's all from me now. This was supposed to be a short video. I don't know why it's longer. It's supposed to be only 3 minutes or 4 minutes. I guess it's only that much. Depends on how my editing is. But yeah, I'll see you guys soon. Bye. Yeah, actually do something on video.
Okay. We all have. Are you recording?
Go again.
GDP 248, and this is our preliminary 5 test. Oh!
Yeah, you did.